right, so recording again, and let's go ahead. Bubble sort. Okay, not because it has to deal with soap bubbles or anything. It's named because the items will slowly bubble their way to the top. The algorithm is pretty simple. It's even simpler, in my opinion, than selection sort, but it's a bit harder to understand why it works exactly, but it's still good. So it's also a bit more efficient. There's ways to optimize it. So let's go ahead and look at our, let's go ahead and generate a random array. So 1, 2, 3, 4, 5, 6, 7, 8. So there's our array of numbers. Okay. Now bubble sort is fairly straightforward. What it does is rather than like selecting something, what it's going to do is that we're going to try to find the biggest item and kind of bubble it to the top. So I think for this example, I'll go ahead and swap 8 and 4. Okay. And it's going to do it by trying to sort stuff along the way as best as it can. So what we do is that we look at pairs of items. So we look at 7 and 2. Then we'll look at this pair, then this pair, and this pair, and this pair, and this pair, and this pair. Okay. So there's 8 items, so there's 7 pairs. So we're going to do basically a loop, essentially to iterate through all the pairs. So let's go ahead and just look at the pairs. So 7 versus 2. And what we do is that basically if the pair of items, just the pair, is in order, we leave them alone. And if they're not in order, we swap them. So 7 and 2, with regards to each other, they're not in order. They would be in order if it was 2 and 7. So that's where we're going to swap it to. If they were in order, we wouldn't do anything, but since they're not in order, we go ahead and swap them. Okay, now we finish that pair, now we go on to the next pair. Okay, 7 and 3, not in order, so we swap them. 3 and 7. 7 and 1, not in order, so we swap them. 6 and 7, that pair in order, are basically, is this a sorted pair? It is not, so we swap them. 6 and 7. This is a sorted pair? No, it's not. 5 and 7. This is a sorted pair. Yes, it is. So go on to the next pair. Okay, we don't do anything here because they're in order, so now 8 and 4. That's unsorted, so we sort it. Okay, and then we made our pass through. Okay. So, and what that did is that this locked 8 basically into the top of the array. Right? What happened here? Well, we bubbled the biggest item to the top. Notice how basically that, it's a bit more in order. 7 especially is closer to the end of the array that it needs to be at. But we're guaranteed that when we run this algorithm once, we're going to grab the biggest item that's unsorted and move it to the top, to where it needs to be sorted. I mean, let's see how that worked, right? Right, 7 was the biggest item, so it was moving basically until it found a bigger item, and then we moved that bigger item forward until we hit a bigger item, then we move that bigger item forward until it hits the end, right? So when we stop swapping, that's because we found a bigger item, right? And so the biggest item will eventually end up at the top. So what we can do then is that we can run this essentially, well, there were 7 pairs of items, so if we run this 7 times, we're guaranteed to sort it because the next time we run it, the next biggest item, 7 will be in place, then 6, then 5, then 4, then 3, then 2, and then we get that last one for free because it just hangs out. Well, I mean, last item just ends up. So let's go ahead and do this again. So 2 and 3 are in order, 1, 3 are not. 3 and 6, 6 and 5, 5 and 6, 6 and 7, 7 and 4. Okay, and then 7 and 8 are already in order. We really don't have to check that one if you're clever about it. So essentially, like the other one, this is going to be a nested for loop. You're going to have a for loop to, if you're doing this the unoptimized version, you're going to basically do this as a single for loop, and then to sort everything, and to basically do that pairwise sorting, and then the outer for loop is to basically do that a certain number of times. Okay, so we ran through it twice. Okay, so we got 7 to the top. If we run through it again, we'll get 6, then we'll get 5, and then we'll get 4, and then we'll get 3, and then we'll get 2. So if we run it 7 times, the number of times the pairs you have, this will work out. Okay, so A lot of times, though, as we'll see, that we could stop earlier. So let's go through another iteration. 2 and 1, they're unsorted, so we swap them. 2 and 3, sorted. 3 and 5 are sorted. 5 and 6 are sorted. 6 and 4, unsorted. And then we could stop here if we're clever about how we program it, but 6 and 7 are sorted. That's sorted. Okay, let's do this again. 1, 2, 2, 3, 3, 5, 5. Okay, 5, 6, right, and we're done with that. And then we could go through it again because again our algorithm says 1, 2. It needs to check again. 1, 2, 2, 3, 3, 4, 5, 5, 6, 7, 7, 8. Right, because your program doesn't necessarily know that it's sorted. Right, if we wrote this naively, we told it basically because there were 8 items, do 7 runs of the inner for loop. You know, that's a solution. Basically, there's 8 items, so run the outer for loop 7 times to look over all 7 pairs. Okay. Another way to do this, though, is that we can detect that we don't need to do any more swaps. We could have a while loop, which basically says we keep running this inner for loop until we get to an iteration like this, where we found that it was sorted. How do we know it's sorted? Well, it's sorted if we run through this algorithm and there's no swaps. So we can run through. If there were no swaps, then it was sorted, so we could just stop right now. Okay. There's a great write-up on bubble sort and selection sort, and the next one I'm going to go over on Wikipedia. So I suggest leveraging those heavily. They've got beautiful animations. Wikipedia here, Wikipedia for sorting algorithms is a great resource.